Penetrating the secrets of the infinitely vast universe, man's oldest dream. In this quest for truth, the two extremes come together, the infinitely large and the infinitely small. Particles from the world's first moments, protons, neutrons, electrons, but others too, much more energetic. They disappeared very quickly after the Big Bang, and no longer exist today in their natural state. The only way of identifying them, recreating a mini Big Bang, and trying to reproduce these particles which lie at the very origins of our universe. This picture is not fiction. It represents what's been happening for several years in the LEP, a giant accelerator 100 meters below ground in a 27-kilometer-long circular tunnel. In the accelerator, at a speed close to 300,000 kilometers per second, bundles of electrons and positrons circulate in opposite directions. A head-on collision is arranged in the detectors installed at various points around the circular tunnel. The particles generated by the shock are not simply debris from the electron-positron collision. They really are new, and are born of the transformation of energy at the moment of collision. The greater the energy available, the greater their mass. In the detectors, these new particles, according to their type, penetrate to different depths the various layers surrounding the point of collision. The resulting image will be analyzed by physicists and may perhaps contain traces of the particles they're looking for. But the energy necessary for the experiment can only be increased beyond a certain threshold in the LEP by technological artifice. Indeed, the faster the electrons and positrons travel, the more they generate their own braking system by emitting light. To be able to create a more energetic collision, capable of generating heavier particles, a completely new machine had to be designed, which will be in operation from 2005 onwards. Today, this machine is under construction. It's the LHC, a much more powerful accelerator that will be installed in the same 27-kilometer circular tunnel. Instead of propelling electrons and positrons, the LHC will accelerate protons, 2,000 times heavier. The physicists hope to be able to identify in the products of the collision particles which explain the origins of our universe. In this 27-kilometer circular tunnel, whose radius can obviously not be modified, the challenge consists of circulating two opposite beams of protons at more than 300,000 kilometers per second in successive bundles, whilst maintaining the protons precisely at the center of the tube containing them. The ultimate objective is to bring about a frontal collision of these bundles of protons in 4 different places, having deviated them from their trajectory to obtain an interaction at the center of the detectors. The only foreseeable solution to maintain the particles in their trajectory is to create a powerful magnetic field along the full length of the proton's route, capable on a continuous basis of exactly balancing the centrifugal force exercised on their mass, a force which will tend to push the protons off their trajectory. In fact, it's well known that any charge moving in a magnetic field is submitted to a force perpendicular to both the speed of the charge and of the magnetic field. In this case, the electric charge is V, which represents the movements of the protons in the accelerator. The magnetic field B, necessary to maintain the protons in their trajectory, exercises a force F, perpendicular to both V and B. It's obvious that any particular shape of the cable which transports the electric current will have a direct effect on the structure of the magnetic field, visualized here using iron filings. An electric current is passed down the copper wire and a magnetic field appears. A conductor laid out in another way creates two magnetic fields with an interaction between them. To guide the two opposite waves of protons in the LHC, a complex magnet has to be built. Moreover, an LHC magnet made with traditional materials such as copper would need to be supplied by several power stations, a veritable utopia. In addition, traditional electric cables would not support the necessary intensity of current. In fact, in a classic conductor, copper for example, the electrons which transport the current, the conduction electrons, are slowed both by successive layers of atoms and by their disorganized progression in the structure of the material. All this friction will bring about heat in the substance, which will end up by melting and burning. This is called the Joule effect. Certain materials, luckily, become superconducting at very low temperatures. That is to say, their resistance is equal to zero. Mercury was the first to be identified in 1911 as a superconducting material. By studying its electric conduction properties, the surprise discovery was made that this metal, at a temperature of 268.95 degrees Celsius, conducted current with no drop in potential, as if all the electrical resistance suddenly fell to zero. Since this discovery, numerous superconducting materials have been identified. The phenomenon of superconductivity, which will suddenly appear in materials at a certain temperature, is better understood today. Instead of knocking against each other in the structure of the material, causing considerable heat, electrons will behave in a different way. At very low temperatures, the interaction between electrons and atoms leads to the appearance of an attractive force between the electrons, a force which can be greater than their natural tendency to repel each other. Ultimately, the electrons gather in pairs, and the entire set of pairs behaves as a liquid, being able to flow freely. It might therefore be said that the material in the superconducting state resembles a giant macroscopic atom, and that superconductivity is a large-scale manifestation of the quantum mechanism whose physical effects are habitually confined to the microscopic scale. That's to say, the single dimension of atoms and molecules.